enduring understanding 1b is all about the interaction between electrons and the nucleus. The nucleus positive charged, the electron negatively charged. And in 1b, kind of describes that as well. Coulomb's law is the key here. I'm assuming most of you have taken physics before, right? Does anybody remember Coulomb's law?
Q1, Q2 over R squared.
Okay, that's the form of the equation in my terribly drawn Q's. What does it mean?
Like the charge of one.
Q1 and Q2 are the charges.
And R is the distance.
And R is the distance between those charges. So I've got a simulation that I found, and I linked to it on the AP notes. So if you scroll down here, we've got the learning objectives that we're going to try to meet here, the problem set that I just gave you. And I've got the Wikipedia page about Coulomb's law. I've got the equation here, and this is the simulation we're going to look at right here. All right, so we've got these two charges. One's positive 1 charge, the other one's a negative 1 charge, and it's going to plot the force between those as a function of the distance between them. And so I can drag it around, and you can see the arrows are giving us an indication of how big that force is. When I let go, it puts a little dot on the graph. You can see as I'm pulling them apart, we're only at 3.6 angstroms here. 10 to the minus 10th meters. As we get closer and closer, the force gets larger and larger. And now you can see from the shape of the graph, hopefully, that this is an inverse function, right? But it's not our normal just 1 over x kind of inverse function. It's changing a bit faster than that, so that's where we get the 1 over r squared here. Okay? But when we think about the interaction between a positively charged nucleus and a negatively charged electron, the two things we have to be keeping in mind are, what are the magnitude of the charges? So Q1 and Q2 are the charges, it's really the magnitude, or how big the charge is. So I can change the charges here, and it changes the force between them. So I can make another graph that describes the relationship between a +2 charge in the middle and that negatively charged electron. So what is it about the nucleus that's going to determine the magnitude of the first charge? How many?
Electrons?
Electrons? The nucleus?
Protons?
How many protons are in the nucleus, right? So the positively charged protons in the nucleus, that's represented by the atomic number, right? And we're really going to focus, for what we're going to do here, on an individual electron's interaction with that nucleus. All right? So that's kind of something for all of our explanations that we're going to be using in this unit. We're going to be using Coulomb's law to explain trends. You guys have probably learned about trends before. Size, atomic radius, maybe even ionization energy, the trend, right? But you probably just had to memorize how it changes from one direction of the periodic table to the other. We're going to have to be able to explain those trends. Why does the ionization energy increase when we go left to right on the periodic table? We're going to use Coulomb's law to help us explain it. Okay? Any questions about Coulomb's law? How many people have heard it before? Okay, So most people are reasonably familiar with it from physics. We're not actually going to do any calculations with Coulomb's law. It's going to be all qualitative. So just thinking about what happens when I change the number of protons in the nucleus. Well, it's going to change the magnitude of Q. All right, what happens when I change the distance that the electron is from the nucleus? That's going to change my R. Okay, so let's go ahead and look at some ionization energy data. My favorite website here, Wikipedia. The page is the ionization energies of the elements data page. So notice right on top here, it's giving us the units, because we've actually got some slightly different values for each of the elements. So these top ones, 1300, 1312, what units is this in? Use and well give former in the unit kilojoules per mole. So how many kilojoules of energy does it take to remove a mole of electrons from that element? Okay. Ionization energy is telling us how much energy does it take to remove those electrons. And the CRC, you guys know about the CRC? The Bible. Yeah. Look at that bad boy. A handbook, Chemistry and Physics by the Chemical Rubber Company, which doesn't exist anymore. Okay, but they made this nice book for us that's got all kinds of data in it. If you ever have trouble falling asleep at night, bust this thing out and start reading through azeotropic data for binary systems. You'll be asleep in like half a second. Okay, so that's where these bottom numbers are coming from. Those are in electron volts. So one of the ways they measure these ionization energies is to take a sample, turn it into a gas, and try to pump some electrons through it until the electrons are going through that gas with enough voltage that when they hit the atoms of gas, they start to knock electrons off. So you'll actually see a difference. I believe they measure sort of how easy it is for the electrons to go through that gas. If the gas is neutral, it's going to be hard to get electrons to go through that too. But once you hit this ionization energy and start knocking electrons off, the gas becomes conductive. So you can tell when the gas gets conductive that you've knocked electrons off. You measure how many volts that takes, or in this case electron volts, and that's where they're getting these numbers right here. All right? So, what we're going to need to be able to do in this unit is to look at data. We're going to need to think about trends in the data. We're looking for patterns. We're looking for relationships. So we have to be able to explain the trends. Another thing we'll actually have to be able to do is to figure out what element it is, just given some of this data. All right? So we can see hydrogen. Hydrogen's got one proton and one electron. Right? To remove that electron from hydrogen takes 1,300 kilojoules per mole of hydrogen atoms that you want to remove the electrons from. We go to helium. Helium is about 1,000 kilojoules per mole higher. Why does it take more energy to remove an electron from helium than it does from hydrogen?
I have an idea.
Donna, what are you thinking?
Because the helium has one orb around it, and taking one of them. I forgot.
You're going helium to lithium? Okay, so you're already using some words that we're going to talk about in a minute. He's talking about orbits, right? You guys are all familiar with the Bohr model? Okay, so if you think about the Bohr model of the atom, which has the nucleus in the middle and it has these rings that are the paths for the electrons, we're going to be talking about those. But I was asking about hydrogen and helium. And if you remember anything about that Bohr model, if you've got your nucleus in the middle, that first ring, we call it an energy level. How many electrons can it hold? 2. So So actually, hydrogen and helium's electrons are both in that first ring.
Helium has already two and it took reached happiness. And hydrogen,
You said helium already has what?
like it's reached happiness.
I'm so glad you used that word. Happiness. Yes. A very easy way to help first-year chemistry students remember trends. It's how they become happy, right? Helium's so happy because it's filled that first ring. If you put happy down on a test, especially on the AP test in May, you are not going to get any points, okay? Because helium and hydrogen, neither of them have a nervous system. So they cannot be happy. What about stability? Well, what does stability mean? That's just kind of a word that kind of like is like happy.
Doesn't it mean like they're stable, like they're...
Remember what I said. Every explanation we're going to use in this unit is going to be based on what? Coulomb's law. Okay, so if you're not explaining it with Coulomb's law, you're not doing it right. Okay? So what we have to think about is what is really the fundamental difference between hydrogen and helium that's going to appear in Coulomb's law. Charges. Right? The distance is going to change a little bit because they don't have exactly the same size, but really, since both the electrons in hydrogen and helium are in that first ring, distance is going to be about the same. What's going to be very different, though, is the charge. Because hydrogen only has one proton in its nucleus, helium has two. Okay? So that's the reason that it takes almost twice as much energy to remove an electron from helium than it does from hydrogen, right? Because there's twice as many protons. If we go to lithium, it's a lot lower. Crap, I guess that explanation's out the window, right? Because lithium has 3 protons, right? So if lithium has 3 protons, shouldn't it take even more energy to remove an electron from lithium than it does from helium? Well, yeah, so we know from the Bohr model, once we fill up this first ring with 2 electrons, now lithium is going to have an electron in the next ring. So the electron that we're removing in lithium, the one that is represented by this number right here, is actually the outermost electron. So that's an important thing to keep in mind when you're looking at ionization energy data, is that these things are going to go in order from the easiest to remove electron to the hardest to remove electron. And the easiest to remove electrons are going to be the ones on the outside. Why? Because they're further away. And Coulomb's law says as this distance gets bigger, the force between those particles gets weaker. Question?
Okay. This is like I guess like a trend of electron question. So for hydrogen it has 2 electrons. For helium it also has 2. Lithium has 3.
Wait, hydrogen only has 1 electron.
It only has 1.
That's why there's only 1 value here.
Does it always match the number of protons?
So the number of ionization energies on this table matches the number of electrons that that element has. And
Will it always
the number of electrons that it has will equal the number of protons that it has at the neutral atom. Now, let's just talk about why there's 2 different values for helium for a second, right? So we have 2372 listed, and then we have 5250 listed. Why the heck are there 2 different values for helium? They're describing how much energy it takes to remove each electron. So when we look at this number for helium, this one right here represents taking a neutral helium atom removing an electron and being left with a helium ion. When we look at this number represents removing an electron from helium that's already had an electron removed from it. So this would be represented by helium plus, where we're taking away that electron and forming helium 2 plus. And if you look at the data, you can see that the ionization energies always increase. It always takes more energy to remove the next electron than it did to remove the one before. Okay, because we're removing it from a more and more positively charged ion. All right, so again, if we look at lithium, this first one is taking neutral lithium, turning it into lithium plus. This number here is taking lithium plus, removing an electron, turning it into lithium 2 plus. And this last one is taking lithium 2 plus, removing an electron to form lithium 3 plus. Okay, so you're always going to see these numbers increase for a particular element. All right, and then again, we can see the trend as we go down. Hydrogen was 1312, helium larger, 2372, and then lithium drops to 520. Again, because in lithium, we are now removing an electron that's further away. But once we remove that farthest away electron in lithium, notice what happens when we drop back down to that first ring and try to remove an electron from the first ring of lithium. If you think about it, lithium plus 1, what's that going to look like? Lithium plus 1 now has that electron removed, right? And it's got 3 protons in its nucleus. Well, helium had 2 protons in the nucleus and 2 electrons in that first ring, right? So now, when we're looking at the second ionization of lithium, as far as the electrons go, it's similar to the first ionization of helium. But look at the number. Right? It takes more energy to remove that electron in lithium. Right? Just the first electron that we're trying to remove from this inner ring, it takes more energy to remove it from lithium plus than it does from helium. Why? More protons. So Coulomb's law, we can think of maybe Q1. Let's call Q1 the number of protons. Or we could say that's the charge of the nucleus. Right? And then Q2 is the charge of an electron. Is the charge of the electron going to change? No. All these electrons are identical. So really, what we're talking about is the charge on the nucleus. How does the number of protons in the nucleus affect how hard it is to remove an electron from it? Now, when we try to remove that next electron in the first ring of lithium, it takes 11,000. So we jumped from 500 to 7,000 because we were jumping from the second ring down to the first ring in terms of what electron we were moving, right? But then when we go to the third ionization of lithium, it's still in that closest ring. So we still see a jump, we still see an increase in energy, but it's not as drastic of an increase as we saw when we changed rings. Okay, so every time you change a ring, you're going to see a big jump in energy. That's one really, really key idea in helping identify what element we're talking about. We're going to look for those jumps. Those jumps are going to tell us when we're changing energy levels. Okay? If we go down to beryllium, beryllium is different from lithium in that it has 4 protons in the nucleus, and it starts with 4 electrons. 2 in the first ring, 2 in the second ring. So, notice beryllium's first ionization energy, right? This column is all the first ionization energy. I'm going to move this down so you can see it a little better. Beryllium's first ionization energy is larger than lithium's. Why?
Because it's on that second. And there's 2 electrons like together on that second.
This is beryllium, right? Where do I want to go with? Yeah, if we think about the location of the electrons we're removing in beryllium and lithium for the first ionization, they're both being removed from the second ring. But the key reason that beryllium is harder to remove is the difference in the number of protons. Okay? So 3 protons here, 4 protons here, same ring, more protons, it's going to be harder to remove them in beryllium. Okay? And we can see, even when we remove an electron in beryllium, and it has the same configuration of electrons as lithium does, it's still harder to remove that electron in beryllium, right? So again, if I look at the second ionization of beryllium, I've already removed 1. So now the second ionization energy, we're removing it from beryllium plus, and with the exception of that extra proton, it looks just like lithium. Okay, but that extra proton, according to Coulomb's law, is going to make that electron harder to remove. Okay, so this second ionization of beryllium is larger than the first ionization of lithium. Okay, so 900, then we get almost a doubling to 1700. Okay, but look what happens when we try to remove the third electron in beryllium. Well, second ionization energy, we've removed the second electron. Now the third ionization for beryllium, where are we going to remove it from? We got to remove it from that innermost ring, right? So because we're jumping down to an inner ring, we're going to see a huge jump in the energy that it takes. So from 1700 to 14,000, almost 10 times harder to remove that electron in a smaller ring than it was for either of the ones in that outer ring. Okay? Questions on it? Okay. So we can scroll down a little bit more. And we can see if we look at carbon here, again, well, beryllium to boron to carbon, uh-oh. What happened there? Remember, all the explanations I was just giving, we were saying more protons, more protons, more protons. Well, boron should have more protons than beryllium, and yet it's easier to remove that first electron in boron than it is in beryllium. What's up with that? Well, hopefully in your last class you went a little bit beyond the Bohr model. Yeah? No? Only Bohr model?
Probably the new one.
Okay. So it turns out that the Bohr model, which you might have learned about in 8th grade or maybe in your first chemistry class, the Bohr model sets how many electrons can fit into each of these rings, what we call energy levels. And according to the Bohr model, 2 electrons can fit in the first energy level. How many can fit in the second? 8. 2, 8, another 8, then an 18, then an 18. Okay. But it turns out the Bohr model is not exactly what's going on. So we're going to move beyond the Bohr model. We're not just going to talk about these energy levels or these shells of electrons, because it turns out there are subshells. All these 8 electrons that Bohr would have said are in the second energy level, it turns out that they're not exactly in the same spot. So we're going to have to talk about what are called subshells. The first energy level only has 1 subshell. The second energy level actually has 2 subshells. Did you guys do electron configurations at all? 1s2, 2s2, 2p6? How many people have heard of those before? Okay, about half of you. So we're going to do that actually in the next unit, so I'll explain more about what's going on there. But we can see in the data from beryllium to boron that there's something weird going on. Boron has 5 protons compared to beryllium's 4, so if that was the case and Bohr model was completely correct, it should be harder to remove an electron in boron than in beryllium, because they're both going to be removed from this second energy level, or the second shell, but boron has more protons. Well, it turns out that really there's sort of subshells. So it's almost like there's 2 shells of electrons that are close, but not quite the same. And one of those shells in the second energy level holds 2 electrons. The other shell actually holds 6. A lot of times we use this notation N. N equals 1. That means the first energy level. These rings here would be under N equals 2, the second energy level. But within that second energy level, we have 2 sort of subshells, 2 divisions of that second shell of electrons. One being a little bit closer than the other. And so the explanation for boron's ionization energy being less than beryllium is that boron has 4 electrons, so a filled first shell, a filled subshell of the second energy level. Sorry, beryllium has 4. Whereas boron, with 5 electrons, fills that first ring, fills that second ring, but then its next electron is in a slightly larger subshell of that second energy level. So it is slightly farther away than the electron was in beryllium, which makes it slightly easier to remove. So we see a little bit of a dip for boron. Now why don't we see a dip for carbon? Because carbon should fill the first ring, it should fill that first subshell of the second set of electrons, and then it should have 2 in that next subshell, right? But remember, as we go through here, we're adding more and more protons. So even though this electron in carbon is being removed from a slightly larger shell than the first electron we were removing in beryllium, one of these, it's also got 2 more protons than beryllium. Okay, so the increase in proton at that point sort of counteracts any distance effect that we have from these subshells. Okay, but let's go across and look at carbon's data. And let's think about which electrons are being removed. Okay, so we have 1,086 kilojoules per mole to remove the outermost electron. So that would be one of these. Okay, so now we have carbon plus. If we try to remove another electron, it takes 2,300. That's this one here. Next electron we try to remove takes 4,600. That's one of these right here. Then 6,200. That's this one right here. So now we've removed all of them from this second shell. Now when we go to the next ionization, now we're going down to the first shell and look at the jump from 6,000 to 37,000. Okay, so when you look at these data, the jumps that you're seeing are showing you jumps between the different shells of electrons in those atoms. We're also going to be able to look at some of this data and understand that the shells are further divided into subshells. Okay? Actually, eventually, we're going to have to talk about this as well. If you look at nitrogen, nitrogen takes 1,400 kilojoules per mole to remove. Oxygen, only 1,300. So what the heck? Boll, are you lying to us? Because what did I say? I said that the first shell holds 2. The second shell holds a total of 8, but it's split up into 2 subshells. The first subshell holding 2, the next subshell holding 6, right? But if we look at the difference between nitrogen and oxygen, nitrogen's going to fill up that first one. How many electrons does nitrogen have, by the way? 7, right? If that's its atomic number, it's going to have 7 electrons, 7 protons. So 2 in that first ring, or first shell, 2 in the first subshell of the second shell. What am I at, 4? So now I'm going to put 3 electrons in that second subshell of the second energy level. Oxygen is going to look similar. 1, 2, 3, 4, 5, 6, 7, 8. So hold on, that seems kind of strange, right? Because we're still filling up that second subshell of the second energy level. We should have more protons when we go from nitrogen to oxygen, and yet the ionization energy decreases. So maybe there's another subshell in there, right? Maybe what I said about there being only 2 subshells in the second energy level is actually not true. Well, it turns out it is true. Okay, but there's some more effects here. How do we know that there really are just 2 subshells in the second energy level? Well, there's another type of experiment we can do. Ionization energy data, in order to remove all of these electrons, like I said before, you have to remove them one at a time. So you remove 1 electron, then you remove the next electron, but you're removing it from an already ionized atom. So again, we talked about how the energy increases every time because you're removing it from a more and more and more positive ion. But we do have evidence that leads us to believe that in the second energy level, there are only 2 subshells. And the data we have comes from what's called the photoelectric effect.